In this video, we will continue our discussion related to the calculus of parametric curves by specifically thinking about equations of tangent lines. So previously, as we've discussed, if we have a parametric representation of a curve, that is these functions f of t and g of t that represent the respective coordinates x and y, we now have formulas for dy dx and the second derivative of y with respect to x. And a natural question one might ask is, do we still have the same geometric interpretation of these quantities? That is, does the derivative dy dx still tell us the slope of a tangent line? And does the second derivative still tell us something about concavity? And the answer is absolutely. So for example, if we have a point on our curve, it's reasonable to draw the tangent line to that point. And let's go ahead and say that this point corresponds to the parameter value t naught. So what we would have to do to find the equation of that tangent line is we would need to know the point where it hits the curve and its slope. The point where it hits the curve, we take the parameter value t naught and you plug it into the respective parametric equations. So that would be f of t naught comma g of t naught. And then the slope of this line, we would take the derivative and we would evaluate it by replacing each t with t naught. And once you have a point and a slope, you would have the point-slope form of the tangent line. So let's look at a few examples. In this example, we will find the equation of the tangent line to the parametric curve given at the parameter value 2. Now, note, if you go through our previous methods, we could easily sketch a representation of what this parametric curve would look like. But since we've only been asked for the equation of the tangent line, we'll just go ahead and find it. So we need to do two things. We need to know what is the corresponding point. So when t is equal to 2, what is the point we have on our curve? Well, to get that x coordinate, we plug 2 in to our parametric equation for x. So that would give us back the point 4. To get the y coordinate of our point, we plug in 2 to the parametric equation we have for y. 2 cubed is 8. Secondly, what we need is the derivative dy dx. So recall, dy dx, we take the derivative of y with respect to t, because y is on the top. That would be 3t squared. And we divide it by dx dt. So 2t, and that leaves us with 3/2 t. And the slope of our tangent line is going to be the derivative dy dx, where we evaluate this at t equals 2. And note from a notational perspective, when we see the vertical bar subscripted with a value t equals 2, that is telling us to take this t value 2 and plug it in. So this would be 3/2 multiplied by 2, which is equal to 3. So putting everything together, our tangent line has slope 3 and passes through the point 4, 8. So the point-slope form would be y minus 8 equals 3 times x minus 4. Or equivalently, our slope-intercept form, if we just simplify and bring everything to one side, would be y equals 3x, and we'd have minus 12 plus 8 is minus 4. So let's look at one additional example of finding equations of tangent lines. In this case, we will look at the parametric equations given by x equals 2 secant, y equals 2 tangent. We will find the tangent line when the parameter t is minus pi over 6. So the first thing is to think about what is that corresponding point. When t is equal to minus pi over 6, the x coordinate of the point will come from plugging in to secant. So secant of minus pi over 6 is going to be 2 over root 3, but it's multiplied by the 2 that we have out front. So 4 over the square root of 3. Similarly, for the y coordinate of the point, we need to plug minus pi over 6 into tangent. Tangent of minus pi over 6 is minus 1 over root 3, but we have that extra 2 out front. So minus 2 over square root of 3. So now that we have our point, the second piece of information we need is the formula for the derivative. So dy dx is dy dt. The derivative of 2 tangent is 2 secant squared. Divide it by dx dt. And the derivative of x with respect to t is going to be 2 secant t tangent t. And crossing off a few terms, we're left with secant over tangent, which simplifies to being 1 over cosine divided by sine over cosine, which is equal to 1 over sine. So dy dx, after this simplification, when we plug in t equals minus pi over 6, what we are going to get back is 1 over sine of minus pi over 6. And sine of minus pi over 6 is minus 1/2. So that ends up being minus 2. Therefore, the equation of the tangent line to the curve would be the line passing through the given point with slope minus 2. So in point slope form, this is going to be y minus a negative 2 over root 3, so plus 2 over root 3, equals the slope minus 2 times x minus the x coordinate of the point, 4 over root 3. And this doesn't simplify overly nicely, so I'm going to go ahead and just leave it in this point slope form.